be able to see that Lab07, right? Lab07. I posted here. I just posted today. So refresh the web page. If you don't see Lab7, refresh it or delete the cookies of the browser. You'll be able to see it. Okay. So I listed most of the questions on the website in Lab7, inLab07, right? So the first few problems for the inLab part of it is regarding BJT calculations, currents and voltages. It's very simple to do, but if you haven't learned it, it could be challenging. I'm going to go through this really quick today, so make sure you are good on that. So looking at this schematic, okay, so what is given is, let me draw it on the paper as well. So RC1 is given, it's 3.3 volts because that's a 3.3 volts device. Okay, so that's logic 1. RC1 is given with the logic 1. And the base, what is base? This is base. Base, collector, emitter, base. It's just name the terminals of the BJT. BJT, bipolar junction transistor. Okay? And VB is 1.6 volts. How much current is flowing through the 300 ohm resistor? Which is the 300 ohm resistor? It's over here, 300 ohms. Okay. Right? What's the current flow through it? Ohm's law, right?
Yeah, 3.3 minus the 1.6 over 300.
Exactly. Thank you. That's problem 1 in the inLab. Problem 2. Go to the graphs at the end of the technical document for the red LED. The red LED is interesting. It's never being used, but it's being soldered on a board. Oh, it doesn't have a resistor with it. So that's the red LED. Don't get confused with the IR LED on the top. So got another IR LED, right? That's IR LED. It's infrared. This is a red LED, the visible range, operating in the visible range. It's just a power indicator. I think whenever it sends a pulse, the intention of this design was, since you cannot visualize whatever is being emitted by the IR, it's the invisible range. So it's trying to, whenever there's a positive pulse, it's going to blink this LED. Okay, so you can see something getting sent. But eventually this one doesn't blink at all for some reason. It's probably because the current too low or something. I don't know. I never saw it blinked. Probably it's blown up on my board. Anyway, but there's a question about it, which is if you look at the graph. So I got a snapshot on my website and trying to show you that, right? Okay. Okay, so the question is, how much current flows through the red LED at 1.6 volts? So what's the voltage across it now? There's no resistor, keep that in mind. I'm crossing that off. So there's no resistor, right? So 1.6 volts across it. What's the current going through it? So it's asking to refer back to here, right? Okay, there's a snapshot from the data sheet. So 1.6 volts, 4 voltage. What does 4 voltage mean? A diode, it's an anode, it's a cathode, right? So if you have a voltage plus at the anode and a minus at the cathode, it's called forward biased. Okay, so because this is the pin junction, and because of diffusion, and there's a built-in voltage. So for diodes, you have to overcome that built-in voltage in order to drive a current across it. That's why for the forward voltage, it has to be bigger than a certain threshold voltage. So if you look at this diagram, what's the threshold voltage? 1.6 volts, right? After 1.6 volts, you start getting current. Before that, it's all zero. There's no current, right? It's just a one directional conductivity, but also it has a threshold voltage across it. It has to be bigger than 1.6 volts in order to transfer current from the anode to the cathode. Okay? Question number 3, assume that the voltage drop from the base to the emitter, okay, from the base. I'll draw another one. Very quick quiz question. What's the name of this node?
Base. Collector. Emitter.
Okay. So from the base to the emitter is 0.8 volts. Why it drops? It just drops. It's a p-n junction. It's a built-in voltage. It's going to drop. It's NPN. It's getting too deep in microelectronics. Don't want to cover too much about that. Waste of time. So it's a p-n junction. It's the PN. So the p-n junction has a built-in voltage. So it has to overcome this voltage in order to transfer current through it. So it's a 0.8 fixed. Keep that in mind. It's fixed. It's not changing. It's telling you that the voltage is 0.8 volts. And there's a, if you look at the schematic, there's a resistor connected to the emitter, right? What's the resistance? 2.2 ohms. Tiny. Why it's keeping this low? Why is it?
So you don't know what current flowing through it doesn't get hot.
But you do want, this is super tiny, you do want more current. Why? So that's why you can keep your IR emitter strong, right? So you are emitting very strong, high power IR signals. So it's able to bounce back and forth and eventually reach the destination. And sometimes you press your remote of the car knob, right? So it's able to detect it with a certain pretty long distance, and also the garage door remote as well. So it's our signal is pretty strong because you need that to be strong. In that case, most of the IR diodes are actually running a pretty high current. So the one we measured, I think, in inLab07 was somewhere around like 300 milliamps. That was a high current, pretty high current for a diode. Okay, so that's why, one of the reasons why, because it's IR, so we need a high power. Because we have high power, so we don't want to keep it on all the time. So that's why we do PWM. You know, so we are keeping a certain duty cycle, and we don't want the duty cycle to be even more than 30%. Okay, so we want to keep it low. As long as it pulses, the decoder will be able to output a logic 0. So it's not a problem. Okay, as long as it goes up. So we hope it goes down as soon as possible. Keep the duty cycle low, so it's not heating up the LED too much. That's one of the reasons. Another reason, you have IR noise in the air, so you want the pulses that is being coded in a certain type, so it's not getting interfered by other signals. Okay? So this is low because we need a high current through it, so we can output high power through the IR light. Right? So it's asking that if the drop is 0.8 volts, what is the VE? What is the VE? So here's E, right? So what is VE? Assume VB value from the previous question. So VB is 1.6 volts, right? What is VE? Right? Circuit 1 problem. So got a 1.6 volts being dropped by 0.8 volts. So you know what that is, right? Okay? That's VE. Why it's called VE? Because that's an E terminal voltage. That's why it's called VE. What is IE? What is IE? IE. IE.
Just that voltage divided by the resistor.
Right, that's IE. And question number 5. So the solution is wrong, I think, and so the TAs may give. I already sent it to the TA. I hope the TA will review and correct it, but just in case. It's saying that assuming that all the current through the resistor, which is this guy, flows from the collector, which is here. But actually it's not, you know. It's okay to assume it, but if you assume it, you have to use it, right? So it's like assuming that, but eventually it's not using it. I will draw this for you real quick. You got 3 currents flowing through it. You got IB. It's a smaller current. It's pretty tiny. And then it turns on the channel, and eventually, because here is powered up to VCC usually. Oh, another question. So usually why it's called VCC? But in the past, most of the transistors are BJTs. So these are collectors. It's getting shorted to the power. I mean, one of the C's must be collector, so that's why it's called VCC. But for the more modern digital systems, usually it's CMOS transistors, and this terminal called drain, and this is called gate. This is called source. So the drain is shorted to the power, and that's why it's called VDD, because one of these is drain, right? It's drain. So the drain terminal is powered, and VCC C is usually kind of the collector of the BJTs. I don't know what the other C means. I didn't search for that, but usually that's where this comes from. And so come back to here. So if I have this is like a switch current actually. This is a tiny current flowing through it and turn it on, and then you got a lot of current flowing from the collector. It turns it on. So current reduce the resistance of the channel because you have a voltage power source on the top pressuring current to go down to ground. That's why whenever you flow a little current into the base, it's gonna trigger a lot of current from the top. That's how you are getting the current getting amplified. So if this is input and the emitter or whatever here is the output, so eventually you are getting the pretty big current gain. Usually it's called beta times IB. So beta is usually like a 99. So you're getting almost 100 times of current gain. So eventually you can see this is a KCL problem. You got 2 currents flowing down, right? You got little thing here and big current. So eventually these are being added together to form what? IE. So IE equals IB plus IC. Okay? Keep that in mind. But because this is small, so we can, a lot of times we can, because you know, so IC is like 99 times more than IB. So IB is small. So eventually we can assume that IE is almost equal to IC, right? That's why I think I have to cover it. I don't think TA will teach this, all right? So IE is almost the same as IC. That's why you can assume it. If you look at the problem, it's saying, assuming that all the current from the through the resistor is from the collector. But is that true? No, it's the current here is the current here and also the current from the base, right? But you are assuming the current here is all from the collector. Okay? So it's asking how much current is flowing through the IR LED when this one is on. So where's the LED? Here, right? This is IR LED. So it's asking you that if we assume this current is entirely just this current, we ignore this small current, then how much current is flowing through this IR LED? Any clue on that? Did you calculate IE? We just did it, right? And we are assuming IE is exactly IC. So do you know IE?
It's equal to IB.
No, IE is this. IB minus this drop and divided by the resistor. Okay? So you got IE. If you know IE, do you know IC? Yes, it's assuming IE equals IC. So this is the IE, and it's going to be the same as whatever the current going through the IR LED. Any question on this? No? At this IC, what is the voltage across the IR LED? Yeah, so you know, let's just write it down, okay? This is 0.8 divided by 2.2. Somewhere around like 358. Let's just assume it's 358 milliamps. Okay, let's assume that value. Okay, so if you look at the diagram of the IR LED here, so that's the IR LED's IV curve. So you can look at the current. When the current somewhere around like a 0.3 volt, 0.3 amps, which is this, right? So almost it's about 0.35 milliamps amps. Then you are looking at this is 0.1, right? This is 0.1, and this is 1. So 0.2, 0.3, right? 0.3 somewhere here. So you can find out if you run a current through the IR LED by 358 milliamps, you are getting a voltage drop across it. And what is the drop? You can find from the IV curve. What is the drop? What is the drop? 2 point something volts, right? 2 point something volts. So that's the answer of that question. That's what that means. And then it asks, what's the current gain? What's the current gain? Current gain is IC over remember the current gain I talked about is IB, little current, and then you get a lot of current from the collector. So that's IC over IB will be the gain. Will be the current gain. Do you know IB? Yes. Already did it. See? We did it here, remember? Right? So 0.3 minus 1.6 divided by this one, you got the IB. Do you know IC? Yes, since we are assuming IB is the same as IE. So IE was calculated from here, right? You got a voltage here and Ohm's law, so you got a current. So in that case, you are able to calculate the gain without any problems. Current gain. Why is it called current gain? Because it's gaining current. It's gaining current. A little current comes in, you get a huge amount of current flowing from the top to bottom. That's gaining current, okay? What's it's asking, so in the lab, okay, on Thursday, it's gonna ask you to measure all these values. You have to use the multimeter to probe it. The voltages, calculate the current, and probe the voltages, find the current, whatever. So it's comparing with whatever the theoretical values you already calculate on the paper. So you can draw a table and plugging all the numbers in there, theoretical values, measured values, you know, something like that. Expect this type of problems in the lab. And what's the cutoff? So it's another new concept. What is a cutoff current? So which means if you don't turn it on, just don't flow anything to IB. So this is the curve we're going to look at. See, cutoff. IB0. If IB0 is tiny, like this much, you're not getting any IC, right? Oh, it could be difficult to understand what's going on, right? Let's get into it. Haven't learned that yet, right? So, this is the voltage on the x-axis, which is actually CE. What does CE mean? From collector to emitter voltage difference. So it's basically your power supply, right?
So VCC.
Yeah, VCC. You can assume it's VCC. You don't have anything in between, but actually you have LEDs and resistors, so it's changing the drops. But just whatever from the two rails, right? and that's the IC, which is the current flowing through the transistor. Okay, so what's happening is when you are increasing your voltage difference, after a certain value, it's getting saturated. It's not changing anymore. Okay, it's getting saturated. The collector is not flowing too much more current, even though you increase your collector to emitter voltage. But what dominates after that? Can you still get more current of IC? So the voltage across the two rails, power rails, right, VCC and ground. So you, after a certain point, which is somewhere around here, so it's getting a flat line for IC. So the collector is not flowing too much current across the channel, right? It's going to be the same, keep constant current after a certain voltage. So how can you change IC though? Change IB, okay? See, these are all different IBs. Is IB getting plotted? No, that's why it's confusing. IB is just showing you this is a smaller IB, this is a bigger IB, this is a bigger IB, this is the biggest IB. That's it. If you give a smallest IB, which is too small, so it's not able to turn on the channel, so you're getting zero, almost a zero current flowing through the collector. If you apply a bigger IB, it's still getting saturated after a certain point. However, the IC is saturated at the higher current. So the higher current results instead of here, right? Cutoff. So cutoff means if you have the IB is too low, then the current flows through the collector is too small to be considered. So it's called cutoff. All right. So it's asking that if RC1 is 0 volts, if you turn it up, RC1, yeah, let's look at that one. Here, right? 0 volts. If 0 volts, you have any current going through this or no? No current, right? Yeah, go that way. It's going out, right? So no current going into the transistor, right? So there's no current, no IC. Treating this as 0, cut off. Okay. And VB is 0 volts as well because no current, no VB, right? No VB as well. Look up technical documents for the BJT, find the maximum collector cutoff current at room temperature. Here, maximum collector cutoff current, 10 nanoamps. So what's happening is this current is 10 nanoamps, tiny. It's like a noise. You turn it off, but still flowing current through the channel. It's noise. None of the devices are perfect, right? It's not perfect. It's still flowing 10 nanoamps through it. Assuming the cutoff current flows through the 2.2 resistor, what's the value? So if the 10 nanoamps current flows through here, how much drop is creating across it? Just Ohm's law. And then there are some of the problems that you need to be careful. Okay, your old friend. Let's redo it. Let's repeat it. How?
Period is 1 over frequency.
So get the period first, right? Get the period first. This equals what? Then what? Right? So no problem to calculate this at all. But the solution, if the TA gives a solution telling you a different answer, because they didn't subtract 1 from it. But you know which equation to use, okay? Just let them know or email me. I already emailed them the correct version of the solution to them, but just in case, okay? So you know what's happening here. You have to subtract 1, but they are showing a result in the solution without this getting subtracted, which is wrong, okay? And then 1 microsecond period. What's PR2? No significant difference, right? So it's giving a frequency, it's giving you a time. So 1 microsecond divided by 10 to the 6, convert it to second. And then this is a time equals PR2 plus 1 over 16 megahertz divided by prescaler. And this is a very similar problem it's making in the solution. So if you see a different answer, let the TA know, let me know, okay? This is right. How much the magnitude of PR2 being changed from P, so P counts. So this is another feature being added to inLab07. Another thing you need to investigate. It's like a research project to find out what's the range of PR2 that I can use, or period you can use. So how to do that? Embed this piece is already in the inLab code, okay? You're not changing anything. So you can actually change the PR2 value by pressing a P. So you are increasing or decreasing that. And then you keep monitoring or keep looking at the oscilloscope until you see a incorrect data transmission. That wouldn't be difficult to do, right? Just keep pressing, change it by 4 until you see the data being transmitted by the IR is wrong. That's it. Increase and decrease. So you are asked to find a range, the sweet range in there.
The decoder is best at 38K, but it works at other frequencies?
Yeah.
Okay.
Yep. Anything else? Oh, Lab7. inLab07 is simple. Lab7. Let's take a look at it really quick. The template is whatever I'm showing you here is already provided on the website. Scroll to the bottom of the website, you can see it. Okay? This time, I'm being nicer, it's a PDF. Not a picture anymore. All right. So the only difference is you press S. You press S. It's not keep calling the transmission function anymore. Right? Remember in Lab 6 we have a transmission function. That's what I provided in the template. It keeps calling, put a new index, turn on the PWM LED, transmit it. This time it's running a ISR using timer to control it. So you are still pressing an S. So in that case, what is strategy you can use to do it? Because after you turn on the ISR, especially for timer 1 ISR, it's not depending on a signal being received, right? It's a timer ISR. Whenever the timer is up, it's gonna interrupt. How do you control it? It's gonna running the main code, do it, do it. It's always doing it. So if you don't press S, you are not saying anything, but still interrupt and doing it.
You set a flag for.
You set a flag. That's right. You need a flag. So have a flag on the very top of the ISR. Okay. So the flag is where? Where do you set a flag? It's very logical, right?
Global?
When you press S, you turn on the flag. Makes sense, right? You press S, turn on the flag. So next time it interrupts, the sending flag is on, it's going to do the sending. So for the sending function here, it's already given to you. It's really simple. Nothing else, just turn on the flag. Where is it? I couldn't even find it, too short. Here. Press S, turn on the flag. Okay? So it still keeps interrupting. It's gonna come to the timer 1 interrupt. And doing the state machine, okay? The state machine. So this time state machine is required. Alright? And I'm gonna show you this state machine over here in the picture since I don't have time to go through all the state machine stuff. But we still have on Wednesday to cover it, but I don't wanna wait. Oh, we should have Wednesday and Friday after the full break, right? Because this Lab 7 is due the week after. The week after. I'm gonna change the due date, just to let you know. But I'm gonna show you a picture here really quick. Okay, I'm gonna show you a picture here really quick. Still have 2 minutes. 1 minute. I really don't have to, right? This is rushing, sorry. But just in case someone want to work on this earlier, okay? So in idle, see if the flag is on or not. If the flag is on, move to the next. Then do your, so you have to move to the next day right after this because next time it enters the interrupt, you want to directly get into here instead of here, since you don't want to always initiate the mask. I don't want to rush. So let's talk about that on Wednesday after the break. Okay? Still have time. Have a good break. What's that?
One question.